Today we start about linear operator. Previous class we also discussed about linear operator. Now we start about boundedness of mapping. Okay, boundedness of a mapping. We also known about it, but today we discuss this one. Let f r to r be a function, then f is said to be bounded if its range is bounded. If its range is bounded. That is, there exists k greater than 0 such that mod fx less than equal to k for all x belongs to R. Okay. Now we talk about in another way, if let x dx y dy be matrix spaces. Let C be a non-empty subset of X. Let C not equal to phi be subset of X. Then a function f C to Y is said to be bounded. Is said to be bounded if t of d is bounded for each bounded set d in C. Is bounded for each bounded set d in C. And also this one to be bounded. Also second thing is said to be Lipschitz or Lipschitz continuous if there exists a k belongs to 0 infinity. If there exists k belongs to 0 infinity such that dy tx dy less than equal to k dx xy. Okay, for all xy belongs to C. For all xy belongs to C. Then the smallest constant k for which star hold is called Lipschitz constant of D. The smallest constant k, for which star hold is called the Lipschitz constant. Okay. Now Lipschitz constant of T. Now we going to further every Lipschitz continuous mapping is uniformly continuous. Okay, we discuss about that. We reach the portion. Every Lipschitz continuous mapping is uniformly continuous. This proposition we write this statement: every Lipschitz continuous function is uniformly continuous. Okay, so how we prove it? We prove it so simply: let epsilon greater than 0 and choose delta equal to epsilon by k greater than 0. Then if t if t believes is continuous, believes is continuous, then dy dx dy less than equal to k d of x xy. Okay, then this one less than k multiplied by epsilon by k equal to epsilon if dx xy less than delta equal to epsilon by k. Okay, then then dy dx dy less than epsilon if dx xy less than delta, and epsilon does not depend on x or y, so t is uniformly continuous. Okay, now we discuss about in norm space. In norm space, a bounded, or that means t is bounded, means how we represent this. We represent this in this way: let xy be norm space, then t dt subset of x to y be a linear operator, be a linear operator, then t is said to be bounded, is said to be bounded if there exists k, if there exists k greater than equal to 0, such that greater than 0, such that norm of tx less than equal to k norm of x. Okay, for all x belongs to dt. If in linear space, this one is simple way: if this one is linear, one function is linear and bounded, then in norm space or linear space, this one is continuous. But we now discuss one important propositions. Okay, which propositions shows the Lipschitz continuous functions. Now we write these propositions: let xy be normed spaces, and t dt subset of x to y be a bounded linear operator, be a bounded linear operator, t dt be a bounded linear operator, then leaves this t or lip t equal to supremum of norm of tx by norm of x. Okay, x belongs to x not equal to 0. Then and x belongs to dt. Okay, so how we prove this one? We prove it so simply by definition of by definition of Lifty. We have norm of tx less than equal to Lifty norm of x. Okay, for all x belongs to dt. Now this implies that supremum of norm of tx by norm of x equal x belongs to dt and x not equal to 0 less than equal to Lifty. Okay, so this implies that if you tell about this one is alpha, then alpha less than equal to Lifty. Okay, we mark it as 1. Now going to further by definition of alpha. By definition of alpha norm of tx by norm of x. Okay, alpha equal to supremum of this, that means less than equal to alpha. Okay, norm of tx supremum of this means less than equal to alpha for all x belongs to dt and x not equal to 0. Okay, so this implies that norm of tx less than equal to alpha and multiplied by norm of x for all x belongs to dt. Then alpha is a bound of t. Then alpha, this implies that alpha is a bound of t. Okay. Next, this implies leave t less than equal to alpha. Okay. So alpha from 1 and 2 alpha equal to leave t. That means leave t equal to supremum of norm of tx by norm of x belongs to dt and x not equal to 0. Okay, we prove this simple one proposition. Now we're going to further we do another theorem. Okay, we do another theorem state about that let x and y be norm space and t dt is subset of x to y. T dt subset of x to y be a linear operator, and if t is continuous at a point x0 belongs to dt, then t c to c subset of x dx to y dy is continuous at point x0, and if for each epsilon greater than 0 there exists delta greater than 0 such that ty tx tx0 less than epsilon for all dx x0 less than equal to delta. Okay, so we write this important theorem which says about one important basic basic property of linear operator. Let x and y be normed spaces. X and y be normed spaces, and t dt subset of x and let t dt subset of x to y be a linear operator. Be a linear operator. Be a linear operator if t is continuous at a point x0. If t is continuous at a point x0, continuous at a point x0 belongs to dt, x0 belongs to dt, and that is then t is continuous or uniformly continuous on dt. Then t is uniformly continuous on dt. Okay, that is t c subset of x dx to y dy is continuous at point cx0 equal at point x0 belongs to c. Okay, if for each epsilon greater than 0 there exists delta greater than 0 such that dy dx 0 less than epsilon for all dx x0 less than delta. Okay, now we proved this theorem. This theorem is a simple theorem of for linear operators. Just one linear operator continuous at a point implies that this linear operator continuous on whole domain. So how we prove it? We prove it suppose that t is continuous at x0. T is continuous at x0. Okay, let x be arbitrary point. Let x be an arbitrary point in dt, and let xn be a sequence. Let xn be a sequence in dt such that xn tends to x. Okay, then xn difference x plus x0, then xn difference x plus x0 tends to x0. Okay, by continuity of t at x0 we have t xn minus x plus x0 converges to tx0. Okay, now note that t of xn minus tx equal to equal to t of xn minus x plus x0 minus tx0. Okay, now t of xn minus x plus x0 minus tx0 tends to 0. So t is continuous at x. So t is continuous at x. Okay, so we all understand. So simply this one hold. Just here txn minus x by linearity property txn minus x plus x0 minus tx0, and this one is tends to 0, so t is continuous at x. Okay, so we prove this one. Now erase these portions and going to another proposition, another important propositions of linear operator. Okay, another, this one is also an important theorem, and now we discuss about one important propositions of linear operator. These propositions tell about that if t is bounded on a ball, then t is bounded on whole. Okay, if t linear, so this one is possible. So we write the statement of this proposition first. Let xy be non-linear space and t dt subset of x to y be a linear operator. Be a linear operator. Okay, then the following are equivalent. Then the following are equivalent. First, t is bounded. Second, t b10, that means one open ball of radius 1, image of this open ball is bounded. Image of this open ball is bounded, then t is bounded. This one is an important proposition for linear operator. So we prove it now. We first prove A implies B. Then we suppose T is bounded. We let T is bounded. Okay. Then there exists a constant. K greater than equal to 0 or greater than 0 such that norm of tx less than k norm of x for all x belongs to t. Okay, then this implies that norm of tx less than equal to k if for all x belongs to b10. Okay, because here this implies that norm of x less than 1. So tx belongs to bk0, here also close to interval 0. Okay, and y. So and for all x belongs to b10x. So first is t, so t v10 is bounded. Now we're going to further discussion about now we're going to further discussions. B implies A. Okay, how this one proceed? Suppose that suppose that t t v10 is bounded. We write it short. Okay, then then let x belongs to dt. Okay, and y construct x by norm x by norm x not equal to 0. So then y belongs to b10. Okay, now since tb10 is bounded, since tb10 is bounded, so there exists constant k greater than 0, such that ty less than equal to k, such that norm of ty less than equal to k. Okay, for all y belongs to b10. Now we proceed further. We erase this above portion. Okay, ty less than k, this implies that t of x, norm of x, norm less than equal to k for all x belongs to dt. Okay, this implies that 1 by norm x, norm of dx less than equal to k for all x belongs to dt and x not equal to 0. This implies that norm of dx less than equal to k norm of x for all x belongs to dt. Okay, this implies that t is bounded. So we prove these important propositions about linear operator. Okay, now we're going to further discussions. We're going to further discussion about linear operator. Now we discuss one example. Okay, one simple example of linear operator. Let x inner product be an inner product space, okay, over R, and let A belongs to X, and define Tx to R by, and define Tx to R by Tx equal to inner product of Ax, x belongs to X. Then T is linear, then first T linear, and second T is bounded with norm T less than equal to norm or equal to How we do this? We know about that T is linear, but we see that here first for sums. If xy belongs to x, then T of x plus y equal to ax plus y equal to ax plus ay equal to tx plus 2y. Okay, now t is bounded. Now norm of tx equal to norm of inner product of ax less than equal to norm of a norm of x. Okay, hence this implies that norm of t less than equal to norm of a. Okay, now we're going to further or next. We know about that t is bounded. Okay, we know about t is bounded, then norm of tx less than equal to norm of t norm of x for all x belongs to x. Then put x equal to a, then norm of a square less than equal to, that means here tx equal to a equal to norm of a square. Okay, less than equal to norm of t norm. This implies that norm of a less than equal to norm of t. This one is 2. So 1 and 2 we get, from 1 and 2 we get norm of t equal to norm of a. Okay, and obviously this gives t bounded. So we prove this problem so simply. T is linear and T is bounded. So today we stop here.